For those who were not here yesterday, I would like to briefly introduce myself again. So my name is Thomas Lucyshyn. I studied polymer engineering and science at our university, Montan-Universität Leoben in Austria. And I'm currently associate professor for polymer processing at the Institute of Polymer Processing, which is part of the Department of Polymer Engineering and Science here in Leoben. And today's topic that I'm talking about is some introduction to polymer processing, scratching basically on the surface due to the limited time and also to this heterogeneous audience. But I still hope that everyone gets an impression of what we're dealing with and what are the challenges with polymer processing and which methods we have. So the content of my lecture will be first a short introduction, some terms and definitions. I find it's important to know them. Then I want to go into some basics of polymer rheology because according to our point of view, it's very necessary to understand the material behavior that you are processing. So it's not only about machines and mechanical engineering, but we're focusing more on the material, on the polymer, how it behaves in processing it. Then comes the major part of these really principles of polymer processing, the different processing methods and the products that are produced by that is starting from extrusion, pipe extrusion, film extrusion, then blow molding, thermoforming, injection molding, and also, of course, recently very strong developments in additive manufacturing. And at the end, I will summarize and give some conclusions. Right, let's start with an introduction. So we heard that already in the previous lecture, so I don't have to tell about this. So we have polymers consisting of macromolecules, which are built up of different monomers and then creating those nice polymers. So we have long, very long chains. This other picture demonstrating this. So depending on the Lego bricks, we have different Lego bricks, and based on how we assemble them, we get different polymers with different properties. And we have different colors, we get different properties, and then we can even, using copolymers, mix the properties. So there's a huge variety of polymers and property profiles which we have. And that also has an influence on the processing conditions that we need. But still important to know these long molecular chains have also some influence on the material flow behavior. Also, the morphology of polymers is relevant and necessary also in terms of processing from the processing point of view. So we had this already in the previous lecture. We have, on the one hand, we have thermoplastics, and on the other hand, we have so-called thermosets, which are like elastomers and duromers. The thermoplastics can be further distinguished between amorphous materials, which have this very unstructured state. So all those molecular chains are entangled, but not cross-linked. So that's important. So they are basically not chemically bound, but just physical entangled. And one example of that is acrylic glass, for example. So amorphous materials are typically also can be transparent, whereas semi-crystalline materials, parts of the molecular chains are able to arrange themselves in crystalline structures, but not all of them. So you will not find a polymer which is perfectly crystalline, so therefore we call them semi-crystalline. You will always have some imperfections within, and that are those unstructured amorphous phases within those crystallines. One example is typical applications. The mechanical properties are typically better or very good for semi-crystalline materials, and typically they are not transparent. So that's the thermoplastics. Once again, the main point is that they are not, the chains themselves are not linked to each other in a permanent link. Whereas for the duromers or elastomers or thermosets, as they are called, we have crosslinks, chemical bonds between the molecular chains. And depending on the number and the density of those bondings, we get different properties. So if we have very few connecting points, then it's quite an elastic material behavior. And we have rubber, basically. So it's like this rubber glove. And on the other hand, if we have a very tight network of connecting points, then it becomes increasingly rigid. And we have really those very hard and rigid materials, which are also quite temperature resistant. And these different morphologies have also an influence on the processing and also furthermore on recycling. So having a look at the different processing paths of thermoplastics and elastomers, we have on the one hand, the thermoplastics typically starting from pellets or powder sometimes. The point is that thermoplastics, as the name says, we have to heat them, to melt them, then they become plastically deformable. So we have to melt them. A typical processing range is in the range of 200 to 300 degrees C for most of the polymers. There are, of course, some at lower temperature and also goes up to 450 degrees for some specialties, but still the majority of polymers will be processed in this range. In the melt state, we can then shape the material into the desired shape. And then finally, we have to cool it down. We have the solidification of the melt, and we end up in a product. The really nice thing about thermoplastics is that this process is reversible. So we can remelt, reshape, and create a product. Of course, we are losing properties. So each time we are doing this, there is some damage done to the material because the relationship between heat and polymers and heat is an ambiguous one. We need the heat to shape it, but on the other hand, heat causes some damage to the material. So we have to find a compromise of not too much damage, but still getting nice processing conditions. On the other hand, we have elastomers, or those thermosets. We start with the rubber or liquid state. And typically the shaping happens in the cold stage, so we were still cold. And then heat is introduced to trigger the chemical reaction of the curing. So this cross-linking, this chemical reactions of cross-linking is happening by introducing heat. And then the product is finalized. And here the problem is that it's typically not reversible, so it's irreversible. So once you have your product, which is cured, you cannot just kind of remelt it as you can do with thermoplastics, which is very important to know regarding recycling opportunities, especially mechanical recycling. So typical thermosets are not the champions for mechanical recycling. So you will not be able to use that for mechanical recycling. There are some developments, though, for like retromers, which are kind of deformable one more time, but still the majority of the thermosets cannot be really mechanically recycled. That's important to understand. What can we do? So I'm in my presentation, I'm basically focusing mainly on thermoplastics. So not on the elastomer side and the rubber side. So we are typically starting from a pile of pellets, and based on the different processing methods, we can produce different products from these pile of pellets. So it could be film extrusion on the one hand, like bags or some standard sheets. On the other hand, there is profiles or pipes, or window profiles, pipes for sewage, whatever. Thermoforming is another method where you would typically produce packaging goods. Then we have all those hollow bodies produced by blow molding, and injection molding is for mass production of complex single part, so not continuous products like pipes, but single parts. And then recently, of course, for crazy, weird geometries, we can also use 3D printing, which cannot be achieved by the other conventional methods. Before I go into the processing methods, I would really like to talk a little bit about basics of polymerology. And for that purpose, I would like to first introduce a little bit of an understanding of how polymer is flowing in a processing machine. So we are assuming we have a polymer melt, and we are trying to pump this polymer melt through a channel. Now we are looking here currently at a cylindrical channel, like a pipe. And then we typically have this flow pattern, so that typically polymers are adhering to the wall. That means they're sticking to the wall, basically. And the material, if we apply some pressure, goes there with the maximum speed in the center. So we typically have this parabolic velocity profile of the maximum speed of the melt flowing in the center, and then zero velocity on the surface. And these different velocities within this channel result in a shearing between single layers. So if you imagine this whole material split up into single layers of material just for a model, then you can see that, for example, in the center line, due to the symmetry, those two neighboring layers move at the same speed. So these bars represent the speed. So they have the same speed. So that means between them, there is no shearing because they move at the same speed. There is not a different speed. And that means in this stage, our macromolecules are staying in this quite unstructured state, in this entangled state, because the molecules are not oriented. And as you can imagine, just a plate of spaghetti, if you try to pull out single threads out of this pile of spaghetti, which are quite entangled, it's very hard to get them out. So here the flowability of the material is quite bad. It's quite a high resistance against flow because they are quite entangled. What is happening if we're moving towards the surface? Here we have a big difference in velocities between two neighboring layers. So that means that this layer is, the surface is at zero speed, and this has a higher speed. So that means in between we have kind of, can imagine like friction. If two bodies are moving at different speeds and touching each other, we get some friction in between them. And with this friction we call shearing in the melt state. And what is happening in this area is imagine you have a polymer molecule which is oriented in this way. And now in this layer, the speed is higher than in this layer. So that means that this part with the higher speed is orienting the molecule in this direction, because here it's moved faster. So in the end, the molecule gets oriented in the flow direction. So that means in general, in those layers close to the surface, the molecules are getting oriented and also a little bit disentangled. So in the end, you end up in layers where the molecules are more aligned to each other, which means also it's much easier to pull out or to move them along each other. It's like now the spaghetti in the package, they're not entangled, you can easily pull it out. So it's in the layers to the surface, it's quite easy to pull them out. And this whole phenomenon we are describing is so-called shear thinning behavior. So with increasing shear, which are applying, the material gets thinner. That means basically the flow resistance becomes lower. It's easier flowing. I will come to that in later slides as well. I would like to share a few equations. So I promise this is the only slide with a few equations. So I won't confront you with our beloved conservation equations. So this is really, I think, accessible to anyone. So let's have a look, also distinguish between shear flow and elongational flow. Shear flow is basically happening in extrusion or in injection molding, whereas elongational flow is a topic for blow molding or other process where you stretch the material. So let's have a look at shear flow. Have a look at a very simple experiment. So we're starting with two plates. The gray ones are two plates, and then in between these two plates we have a polymer melt, which is this red one. The starting point would be that we start with a straight cube. So we start with a straight cube of material, and then we are starting to pull those plates with a certain force F and a certain velocity V. So we pull the plates, and the result of this pulling is that the polymer melt gets deformed. And this deformation is expressed by this delta X. So this is the amount of deformation that is happening relative to the gap height. This is the distance between the two plates. And then we can define certain terms and values which are frequently used. If you're talking about polymer processing, you will come across those terms. That's on the one hand, the shear stress acting on the fluid. So that's basically, we have to transfer this force into the fluid, into the deformation of the fluid. And this is happening with the shear stress with the Greek letter tau is equal to the force which is applied in this interface area between the plate and the melt. And that's the ratio of the force applied on this area. That's the shear stress acting against the force of the external force. So we are pulling with the force, and the material tries to work against it with the shear stress acting in this interface. The unit is Newton per square meter or Pascal. Then we can define the so-called shear deformation, gamma, which is basically the amount of deformation, delta X, which is happening relative to the gap height. This is important if you have a very big cube, a very big height, and a very small delta X, then the whole deformation is quite small. So just to show it, if you have a very big cube and you deform it by a small delta X, then the whole cube will just deform like that. If you have a very small gap and you deform it in the same way, then the deformation is much bigger of the cube. So that really makes a difference how big the height is compared to the deformation which is happening. Next, the shear deformation is one thing. Well, there's no unit because it's meter by meter. And then the next important term is the so-called shear rate. Shear rate is just meaning how fast is the shear deformation happening. The dot, the gamma dot, just indicates is a change of deformation with time. So dot indicates a change with time. So deformation happening within a certain time step, delta t. So what we write here is delta x by h is the deformation divided by a certain time step. So how much deformation is happening during a certain time. And we can rewrite this by delta x by delta t is just distance per time is meter per second is the velocity. So in fact, the shear rate can be defined as the velocity, the speed of the flow divided by the gap height. Here the same, if we have a very wide gap, a very high gap, there will not be too much shearing at a certain speed. If we have a very small gap, then there will happen a lot of shearing inside the material, which also causes some heat introduction. And finally, we have a combination or a relation between the shear stress and the shear rate, and that is the shear viscosity. So that's the shear stress divided by the shear rate. And we are typically in processing, we are using SI units for the shear viscosity, Pascal seconds. And the viscosity is basically the resistance against flow. A similar thing we can do for elongational flow. Now we have a different situation. Now the force is acting perpendicular to the surface and stretching the material, so not deforming the material sideways, but in the length direction, if you want. We have an initial length L0 and then a deformation of delta L, so an elongation, and then a cross-section A0 again, and the force acting onto this material. Then we can define a normal stress. So contrary to the shear stress, now the same equation basically, but a different symbol. Typically we use sigma for a normal stress perpendicular to the surface, and it's once again the force divided by the surface. Same unit, same meaning. Then we can define also some kind of deformation, but now we have an elongation and not a shear deformation. And this typically the Greek letter epsilon is used for that. And that's just the delta L, so how much elongation is happening relative to the initial length L0. And here again, we can define an elongation rate. So how fast is this elongation happening, indicated with this dot. E dot is elongation per time. So once again, delta L by L0 is the elongation per time step delta T. That's once again the speed of pulling divided by the initial length. The unit, by the way, I forgot before also, it's second to the power of -1, which means 1 by second, so reciprocal seconds. And also we can define here a viscosity, a resistance against this deformation is the elongational viscosity lambda. It's sigma divided by epsilon dot. It's quite analogous to the shear deformation. We're mainly focusing now on shear flow because that's the predominant flow also in most of the processing methods. And once again, the viscosity is a measure of the flow resistance. If the viscosity is high, then there's a higher resistance against flow. And if the viscosity is low, then it's a low resistance. Not all materials are behaving the same way. There's kind of different general characteristics of flow behavior. What you see here is the shear viscosity drawn against the shear rate. So that means the faster you are shearing, maybe there is some change in the flow behavior and the flow resistance. Starting with number 1 is the so-called Bingham behavior, which you can find, for example, in toothpaste. That means at very low shear rates, so if there is not much movement, there's a high resistance against flow. It's really behaving like a solid body, more or less. So you need to apply a certain minimum force and nothing is happening. And then suddenly, once the material starts to move, then the viscosity goes down and then you can really have a liquid behavior. And then it starts to move. So if you press on your toothpaste container, nothing happens at the beginning and suddenly it starts to flow. Another characteristic flow behavior is the so-called dilettante behavior, which means that with increasing shear rate, the resistance against flow increases. So if you're moving faster, then there is a higher resistance against the flow. This is one example that can be used for protection gels in clothing. Like here, for example, these protection pads are filled with some dilettante gel. That means at low speed, if you're moving your fingers, that's a low movement, then the resistance is very low, so it's flexible, you can move it. But if on an impact, for example, if you smash your hammer onto it, then it's a very fast deformation rate, and therefore it reacts, it stiffens, and therefore it has some protection effect. Then we have a very prominent characteristic flow behavior, it's Newtonian flow behavior, which means basically it does not depend on the shear rate. So no matter how fast you're moving the fluid, it will always have the same flow resistance. And a typical representative of that is water. And then finally we come to what we are dealing with most of the time is the so-called shear thinning behavior typical of polymer melts. That means at lower movement, if we're moving not too fast, we have quite high viscosities, it's this Newtonian plateau. And then typically at higher shear rates, the viscosity goes down. This is due to this disentangling of the molecular chains. They're aligning to each other, slipping easier. And then we have this decreasing of the viscosity. And this is a very nice property because this enables us basically to do injection molding. Otherwise, with this very high flow resistance, we could never fill very small gaps. So this helps us in doing fast processes in very thin channels. So this is the predominant behavior of polymer melts. It was also mentioned in the previous lecture that the viscosity depends strongly on temperature. So this is just a graph. Once again, the shear viscosity drawn against the shear rate. You see this typical shear thinning behavior again. At lower shear rates, we have high viscosities and it goes down to lower values at higher shear rates. And additionally, see the influence of the viscosity of the temperature. So we have measured this material at 3 temperatures, 170 degrees, 200 and 230. And that's also quite logical. With increasing temperature, the viscosity goes down. It's like honey. If you put it into the fridge, we are here, not at the same temperature, but at low temperature, then it becomes very stiff and viscous. if you heat honey on the oven and it becomes very liquid. The nice thing about this, it can be calculated and shifted together to a master curve. So if we measure the viscosity at 3 different temperatures, we can find equations which can shift them to a master curve. And once we have those coefficients, we can then calculate any viscosity at any other temperature. To give you a better impression of what viscosity and what melt behavior means, I'll show you these nice samples in tubes. So here are different liquids with different viscosities, starting here from 0.001 Pascal seconds, which is water. And then these are different silicone oils with different viscosities, 1, 10, 100, and 1000. And typically thermoplastic polymer melts are in the range from maybe 10 up to even more than 1000, 10,000, and so on. What I'm going to do now is to flip this one, so turn it top down, and you see how the materials follow gravity. Oops, sorry. So nothing is happening. Here's the fluid. Now I turn it around. Of course, the water follows immediately the gravity. This one with 1 Pascal second is also already here. This is still moving. Here you can see that it starts slowly to move. You can also see that it sticks to the wall, and now this parabolic shape starts to develop where the melt goes down. And what you can also notice here, so the liquid is not down here, the liquid is still up here, so that at 1000 Pascal seconds, the material doesn't show any motivation to move just due to gravity. So that means also for our processing, we need to apply quite an amount of pressure to really motivate the material to move. Turn it around again. So just to give you an impression, what do we consider as being melt state? And so not that you think that's like water when you melt ice. Okay, so this is really important to understand the basic principles of material flow. You can, of course, dive much deeper into this topic, but this, I think, should be sufficient to also get a little bit of an understanding what is happening inside a processing machine. Well, then let's go first. The first one is about extrusion. So just show you first some typical extruded products, like could be sheets, plates, wires, films for different applications. In that case, some applications taken from solar applications. Pipes can be foamed to get some better insulation properties. Here we have some pipes which are typically multi-layer pipes, which is, of course, in terms of property profile for the application, it's necessary to have different materials combined. On the other hand, this, of course, from the perspective of a recycler, it's a nightmare. So we have to kind of, separate this, or in the best case, the option would be if we can achieve the same property profile with the same base material, but maybe with different morphologies or different structural differences, but the base polymer chemical structure is the same. But this is really, we are kind of forced to do this in order to achieve a certain property profile. But of course, for recycling, this is not a good option. Other examples for sanitary pipe system in a household, these are extruded, these are not extruded, by the way. On this picture, they are injection molded, these single parts. Another nice example, an extreme example of extrusion is like if you want to apply those huge pipes for protection of like glass fibers over the ocean from Europe to US, they have to be transported and put into place. And in this case, it's not feasible to extrude it in some plant somewhere in the country and then transport the huge pipes to the sea and then transport it. No, they are directly extruded into the sea, cut, and then transported by a tugboat to the marine destination. It's quite some nice extreme example of what can be done. I'd now like to explain a little bit the working principle of such an extruder. So basically an extruder consists of a barrel, which is like a metal cylinder with some heater bands outside so that you are able to heat the material, because we need to heat it for thermoplastic melting. And the core of this extruder is the screw inside, it's this element here. And this screw is continuously rotating, and by rotating, it transports the material from here to the front. We have here to introduce the material, we have a hopper, and typically pellets are introduced to this hopper. The entrance section has to be cooled, otherwise the material would already melt here and the pellets would not fall in, but make a big, huge bunch of material, and it would block everything. Of course, we need a motor and a drive to get this rotational movement of the screw. And in the front of the extruder, we have a die, which is just a symbol here. The die is basically a metal block with some geometry in it, and you pump the material through this die, and depending on the shape of this die, you get a profile, a sheet, a pipe, whatever. So the process, it's like that. So first you're feeding the pellets into the hopper, can be manually, can also be of course automated by some pipes and some continuous conveying of pellets into this hopper. Then in this zone, the pellets are compressed, and then the melting happens in this zone. Then close to the front, there's some kind of homogenization of the melt. And then finally, the melt is pumped through the die. And depending really on which kind of die you use, you can shape your film profile by whatever you want. This is a pipe extrusion die line. Don't worry about those single descriptions. It's just about the dimensions of the whole line. So it's not only about the extruder. We need some other peripheral devices to get a product out of it. So the whole line consists basically of the extruder. The main function of the extruder is just melting and conveying the material continuously. Then we have the die where the melt is pumped through. And then the material comes out, is still soft. So otherwise, if we don't do anything about it, it would just collapse and would not remain a pipe. So we have to guide this pipe through a cooling bath, the water cooling, so that it cools down and stays rigid and keeps its shape. Then as it comes out here, it's still wet from the outside cooling bath, and it has to be dried by an air dryer so that the outside water is removed. And then here is a Holoff unit where it takes the pipe and transports it away, and also a saw. Otherwise we would produce an endless pipe, which we never can transport anywhere. So we have to cut it to pieces and so that we can transport them. That's a huge line, needs a lot of space, and depending on the pipe dimensions, it can really vary long. Just some details how it looks like in such a die. The main job of this die is to distribute the melt coming from the extruder from the bottom. Here is the extruder provides the melt in a circular cross-section, a full cross-section. And now we have to distribute this melt to an annular slit, which forms the pipe, so that it looks like a pipe in the end and not like a bar, a semi-bar. So what it does is basically it transports first there are channels transporting the melt from the inside to the outside. And then we would have like several channels and just some different flow paths there. So we have to distribute it over the circumferences. And this is done via these spiral channels. And what you can see here in the cross-section, at the beginning, those channels are quite deep. So the flow resistance is quite low. So the material likes to go there because there is enough space to go. And there is not a chance to get from one channel to the next. As the flow progresses in the actual direction, those channels are becoming smaller and smaller. So there is a bigger resistance of flow in here. So the material doesn't want to go there anymore because it's a long way around and it's a very small channel. But we open the possibility of the material to change from one channel to the next. So to move more in the axial direction. So not moving in the circumferential direction, but rather in the axial direction. And then at the end, we achieve what we want. We get the material coming out of this round slit in all the same velocity all over the circumference and with the same speed. So that's how it looks like in reality. We have those different channels around the circumference, and then those spiral channels distributing the melt over the circumference. Another extrusion type for another product is for films, and there are two types for films. There's cast film and blown film. This one is cast film extrusion line. So once again, here we start with an extruder. You can add different components to your base material, like fillers, for example, to enhance some properties. Then here we have the classical extruder with the screw melting and conveying the material. Then we can also add some melt filters to filter out some contaminants, for example. And then here is the core part of this is the die, which is it's a slit die. Basically, the slit is a very wide rectangular slit. So the cross section is a rectangle which is very wide and very thin. So like 50 micrometers thick, but maybe 1 meter wide. And that's basically the shape of a film. And this film comes out in a melt state, and immediately after exiting the die, of course, it has to be frozen, otherwise we wouldn't get a defined shape. And then it gets to contact with these huge polished metal rolls, which are cooled. Therefore, it's called also chill roll, it's chilled. And then it freezes immediately upon contact with this roll and stays in its shape. And then there's some additional cooling rolls. You can do some thickness measurement for changing controlling the whole device. There's some post-cooling station. There's some edge trimming because the edges are typically don't look very nice, so we have to trim it away. This is also some waste, internal waste, which can rather easily be recycled because it's not contaminated. It's pure material. And then in the end we have some winder here, and there we have the big rows of the films being ready for shipping. That's how it looks like in reality. So here is the extruder, the hopper, and here the extruder, and that's the die. So that's in that case like almost a meter wide, and then here the film is coming out. So it's the film which is already cooled down. Here is another perspective from the other direction. So here is the die, and here the melt is coming out directly into contact with the big chill roll. And yeah, there's some air knives with some air blowing onto it so that it makes sure that the film gets into contact with the mold and stays there. It's not going in any unwanted direction. Another film production line is the so-called blown film for bags, basically, one production. They're huge, really production lines. So this is like if you would see a person standing here, it would be like this size. Here are the extruders, and it really can be up to like 10 meters high. It's really huge plants. I just want to focus on the most important components of it. So here we have an extruder providing the melt. Then we have the die, which is extruding a very thin hose of deformable melt, which is then blown up by air so that it's expanding. So if you blow from the inside, like into a balloon, you blow the air inside and then it expands. And in order to not to make this expansion uncontrollable, we need this calibration screen, which is around to limit the expansion of this film. And then it goes up. Here it has to be further wind up, takeoff, and flattening again. And in the end, we have a huge winder where you have those film rolls, but they're kind of closed. So before we had like the cross section of this was like a film like this. This would be the thickness in like 50 micrometers and very wide. And now we are getting more or less closed films, which you can flatten, of course. But this would be the cross section of this. That would be the result of this film. So it's a round closed bag, whereas this is just one flat film. Having a look at the die. So once again, we have this multi-layer spiral mandrel die, as I showed you before, but now for more materials. So typically films are not used in one material, but typically have a layer structures or multi-layer in order to have all the requirements fulfilled. It's not, in many cases, not only one polymer is sufficient. We need more layers with different functions for like barrier functions, mechanical properties, and so on. So it's not yet easy to achieve a property profile with one single material. So once again, here the melt is coming out, and then we have this blowing air where the melt is expanded until a certain point when it's freezing. So that's a frost line, so there no further warm deformation is happening. And this is the working principle of such a blown film line. One example of it, so here in that case, we are on 9 extruders providing 9, maybe different materials, or at least 9 different layers for this film. So once again, in the technical point of view, it's very fascinating what is possible. Of course, from the viewpoint of recycling, it's once again a nightmare. So this is really 9 layers of different materials combined in one product, basically, which you cannot really separate easily. That's of course a big problem, and something that has to be addressed, a challenge. All right, then let's go to the next molding principle. It's the principle of blow molding. The typical products from blow molding are hollow articles, like can be simple bottles, but can also be complex shapes like fuel tanks or parts of that, or like on this side, or containers, whatever. And the typical procedure for this method is, there are 2 fundamental phases. The first one is using an extruder again and extrusion of a parison, a kind of preform. I'll show you in later slides how that looks like. And then once again, this parison is blown it's blown fast with air and then gets its final shape. So how does it look like? So this is a cross section of this. We have a mold consisting of 2 mold halves, and inside you can see here the shape of the final geometry, which will be a bottle once it is connected. And the first step is the mold is open. So both mold halves are on the side. And then the extruder continuously extrudes this hose, or it's called parison, which is, when it comes out, it's still elastic, but of course, the viscosity needs to be high enough so that it just does not flow away in an undefined way. So it needs some melt strength that it stays in its shape. Then from the bottom, this calibrating blowing mandrel is entering here. And then on the top and on the bottom, in the next step, it's closed. So the mold is closing, and then it's closed here, it's closed here. So basically this hose is airtight. And now with this blowing air, with this mandrel, air is blown into this parison and inflates it. And by applying this air pressure, then inflates it and expands the material to the shape of the final bottle. So it comes into contact with the mold, with the tool, with the steel. It cools down, and after it has sufficiently cooled down so that it is stiff enough for demolding, then the mold opens again, and then the part can be taken out. So if you're having a look at hollow bodies, you will most probably see some parting lines where the two the mold halves are meeting. So you can find this on typical, if you have like containers for, I don't know, for bathing or so, you will very often find this line on the sides coming from this process. There is a movie showing you how it works. It's a bigger container. So now from vertically, the parison is extruded down to the mold, which is open at the moment. It comes down, then it's closed, it's blown already, it's very fast. So the blowing stage is very fast. Then it cools, and we have to wait until it's sufficiently cold and sufficiently rigid. And then this is taken again with the robot, and the mold is opening. In the meanwhile, you see that the next parison is already coming, because we have to combine here a continuous process of extrusion and a discontinuous process of molding. So it has to be synchronized in some way. So while the one is produced, the next one is already extruded. And once again, the next shaping has happened, takes some cooling time. Then it's opened again. And once again, you see how it's extruded. And so in general, although the product itself is a discontinuous product, but still the extruder works in a continuous way. Okay, that's showing the extruder here, the hopper, the barrel with the cylinders, and the drive. And that's the parts, so really huge containers produced in one process step. Okay, the next process step that I would like to cover is polymer, is thermoforming. So typical thermoforming products are rather simple products and are typically for really for packaging. So packaging of this thing of food, of course, can also be used for plants. And also in the large version, also for a whole pool that is thermoformed, starting from a sheet, and then it gets a final shape of this. How is the working principle of this process? For thermoforming, you typically need already a first step, like you're extruding a sheet or film. So you need a pre-product, which you can then further transform into a thermoformed product. So what you have, either you have already produced your film on this big roll, and then this film is taken from the roll, put into a heating unit. So if you want to shape it, once again, you have to heat it so that it becomes soft and deformable. So there is heated, and then here is the thermoforming station, which I will show you in the next slide in more detail. But basically here the shaping is happening. So the material from this film, from this continuous film, a part of the film is deformed. And here there's a punching station. So the part itself is punched from the rest of the film. And then the parts are stacked here. And also the residual unit of the residual film. So the rest, which is remaining, is taken on here. So just to show you it in the other direction, if the film comes along from this direction, then we might form a cup which has this shape. So here it is shaped. That means that we're getting holes in this film, and this rest of the film is then transported here to this winding unit, and this is the residual material which is the rest of the material, which can, of course, also be recycled internally because it's a pure material. We don't have to separate it from anything else. That's the easier part of internal recycling. In the thermoforming, we can distinguish between so-called positive and negative thermoforming, depending on the shape, on which side you are forming it, because the thermoforming is a one-sided forming. So on one side, the shape is quite defined, and on the other side, it's like kind of, it comes out how it looks like, because there is no active possibility to influence the shape. How does it look like? So in principle, you have the film here in a frame, fixed into a frame, and then this is the forming, the mold, which is typically quite a simple mold. Then this mold is moving upwards, getting into contact with the film, and then you can see here there are holes in this mold, small thin holes or channels by which you can suck the air out of it. So basically you form a vacuum. So if once it gets into contact, there is some air and you suck the air into here by these channels. And by sucking the air in, you produce a vacuum which sucks basically the film over this shape. So it really sucks it over this shape. And now this is positive forming because the shape protrudes out of the surface and it's pulled over it. And that means that the inside of the part, as you can see here, the inside of the part is in contact with the mold, which has a very defined shape. So if you want to have a very defined shape of your dimensions in the inside of your product, then you need to use positive forming. Whereas the outside has some kind of undefined shape because it's really, you have not a big influence on what is happening on the outside, but on the inside you have a very exact shape of your mold. And also the thickness distribution is different. So what comes into contact with the mold in the first step will freeze and then cannot be deformed so much, and then it becomes thicker, and that would be the part that would be stretched last. So just imagine you're starting to stretch the material over this mold, then this part would be the last, which is deformed and has quite a large deformation, and therefore it's stretched a lot, and therefore the material becomes thinner in these regions. If you want to have the outside shape in a quite defined shape, then you need to go to negative forming. It's just the opposite. Once again, you have the fixed sheet, and you have the shape now inside, and you suck not over a protruding shape, but to the inside. So the polymer is sucked here by vacuum. So if you apply a vacuum here by taking out the air here, then the polymer film, the soft polymer film, is now sucked into the shape of the mold and forms the part. So the characteristic of negative forming is that in this case, the outside of the product, so this would be our product, like a cup, then the outside of the product would have contact with the mold, and then you would have an exact representation of the shape of the mold on the outside, and on the inside of the product, you would have some kind of undefined shape, and once again, we have a different thickness distribution. If you compare it, like here, here we have on this corner, we have the thickest region, and here for this part and this corner, we have the thinnest region. So it's the same position of the product, but that depends on the production method. So here we have, you can imagine here is the stretching going on. Like here, you suck it in, and then this would be the part that is pulled here by vacuum at last. So that one will be stretched most, and stretching most means that it's also stretched in this direction and becomes thinner. So this part would be the most stretched part of the product, and therefore you get the thinner regions there. So once you want to produce a part, you need to know where you need your exact dimensions, and based on this, you can decide if you go for positive or negative forming. All right, then let's go. So basically this is also the geometry. As I said, the geometry on the outside is not very much defined. So if you need really very precise parts on all sides of your product, then you really have to go for injection molding, which is a lot more complicated and also more expensive regarding the molds, more complex. Injection molding in general is one of the most important polymer processing methods. The advantages are quite obvious. It's a very direct path from the raw material to the final part. So you have one process step, you put in the pellets, and at the end you get a part which you can basically sell. Normally you have little or even no further treatment of the parts, so the part falls out of the machine ready to use. And it's also possible to use really fully automated process. That's why also in Europe we have quite a lot of injection molding happening still, because there is not too many persons involved. And also what's really good is you have a very high reproducibility of the process, even at very large numbers. So it's a process which is intended to be used for mass production, not for 10 parts. That's not, injection molding would be way too expensive. The part range is very wide, so it can range from very tiny gears in the range of 1 milligram, like this small gear in comparison to a thumb, up to huge containers up to 150 kilograms. And of course, the size of the machines is of course then very different. I would like to show you the principle of injection molding. So that's a principle sketch for such a machine. So on the one hand, we have the so-called injection unit or plasticizing unit. And on the other hand, we have the so-called clamping unit, and they have different functions in the process. Starting with the injection unit, we have again a barrel. So it's basically it's an extruder on this side with a barrel, some heaters outside, and the screw. The difference between extrusion and injection molding is that in extrusion, we have a continuous rotation of the screw and then conveying continuously the material out. In injection molding, the screw is not continuously rotating, but it's also actually moving. So typically, before a new part is produced, the screw is moving backward, collecting material in front of the screw. And then in the next step, the screw is acting like a syringe and pushes the material through the nozzle into the mold. That's why it's also called injection molding machine. The pellets, here's the hopper again. Here the pellets are coming in. Here they are coming in, they are melted, and in the front we have homogeneous melt, which is then further processed into the mold. The clamping unit, we have typically one fixed platen and one moving platen. And attached to these two plates, we have the two mold halves. So a mold consisting of two mold halves forming the cavity. So these two halves are forming the shape of the final product. And then the moving mold half is opening and closing. So this one is moving back so that you can demold the part, and then it closes again so that it's a closed volume, which is then filled with the melt. Additionally, we need to temperature control the mold. So depending on the material which we are processing, we need a defined temperature. If the mold is too cold, the material would freeze too early and we could not fill it. If the mold is too hot, then the cycle time is too long, the productivity is bad, and also the surface quality would maybe not be the best. So we have to find a good compromise between quality and productivity. So this is how such a machine looks like in reality. So this is an injection molding machine in our labs, a very modern one from Wittmann-Bartenfeld. You see here, that's the barrel with the screw inside, which you don't see basically here. There is the hopper. In that case, we have an automated conveying of pellets into the hopper with a gravimetric feeding. And then here we have the two mold halves. So there's one mold half, there's the other mold half now in the open stage. And that's how it looks like. To give you an impression of the size of the machine, I added the size of a person here. So that's typical the size of this machine. And this is for range of, I think, 1,100 kilonewton or 110 tons machine. So it's an intermediate machine size. How is the cycle running? So what's the typical cycle of injection molding? So the starting point is like the screw is typical in the back position. So in front of the screw, we have already collected melt for the next product. Then the mold is closing. The whole injection unit is moving to the mold and getting into contact to have a tight contact with the mold. And there is a channel from the injection unit into the mold. And then the injection phase can start by moving forward of the screw. So the screw moves forward, acting like a syringe, pushing the material through the channel into the cavity until it's completely filled. And now we have to add another step because polymers have the property that they're shrinking quite significantly when they are cooling. So typical shrinkage ranges are linear shrinkage of like up to 2.5%. That means if the mold has a dimension of 100 millimeters and you put the hot melt into it, once it cools down to room temperature, the final product will not have 100 millimeters, but maybe only 98 millimeters. So you have to consider that in your mold construction. That means you have to basically increase the size of your cavity in order to achieve a final desired shape of your part. And in order to compensate this shrinkage which is happening, what you can do is you can press some additional material during this shrinkage phase, during this cooling phase. As long as the material is not frozen yet, so if this channel is still open, you can still push more material in, which means the density increases, the shrinkage will be compensated and you will not get so much shrinkage. But once there will be a point where the gate the channel will be frozen, so material cannot flow anymore, you cannot push any more material into the cavity. And that's the point when you start to feed again, to move the screw backward by rotating it and conveying more material, melting material, and conveying it to the front, so that you're prepared for the next shot. Then you typically need some more time for the part inside to be cooled down sufficiently so that it's rigid enough that it can be safely demolded. Then the mold opens, the part is demolded, can be taken by a robot, can just fall down, taken out manually, whatever. And then the cycle starts again. So mold closes again, injection unit moves forward, injection unit, the screw moves forward and injects the part. So this is running in cycles. It's a discontinuous process. Regarding cycle times, typical cycle times range from very fast processes of small, like closure caps of bottles, for example. We are meanwhile in the range of a few seconds, 2 or 3 seconds each cycle. And we have multi-cavity molds. So in one mold, not only one cavity, like up to 128 parts can be simultaneously molded in one step. And this every 3 seconds, the mold opens and throws out 128 parts. So it's a huge number of parts that can be produced within basically one day. This is a short animation, how it looks like. So the mold is closing, injection unit gets in contact with the mold, then the injection happens, cooling, feeding, moving back, mold is opening, the part is ejected. And now we are looking into the injection unit. So the mold is closing again, the injection unit is in contact with the mold, injection phase, packing is quickly, feeding, going back, opening, demolding. So packing phase is here very short. You don't see them very much in the packing phase. So maybe repeat again. So mold closing, moving forward of the injection unit, injection, packing, feeding, cooling, opening, demolding, and once again looking inside, closing, injection, packing very short, feeding, going back, and so on. This is one possibility to look inside the cavity. What is happening there is we're doing a lot of simulation, so it's possible to simulate the filling phase, having a look at the temperature conditions, also at shrinkage and warpage. And this is a nice possibility to do some front loading. Otherwise, such a mold for a machine can be quite expensive, can even be more expensive than a machine around. So if you produce a mold which does not work, then it's quite a lot of time and money wasted. So if you can use simulation in advance to recognize potential errors, you can optimize your process and your product before you build a real physical metal mold. Okay, the last process I would like to show you, it's really gaining increasingly more importance. It's the so-called additive manufacturing, also known as 3D printing, although this is one term for many processes. Some introduction. So why do we want to use additive manufacturing compared to other conventional processes? It's of course really enabling us to produce very complex shapes, which you cannot ever produce with conventional methods. It's also about individualization of single products. So if you want to have this helmet produced, this one in this shape and color configuration and the next one in the other color configuration, then you cannot do it in injection molding. So injection molding is really, you produce one mold and then you produce 1 million parts of the same size and shape. You can do something with the color, but not in that way. And it's about a fast realization from the project idea to the physical part. You have some CAD drawing, some idea, and then immediately go to the printer and immediately a few hours later you have your part. Mind you, fast means only from the realization from the project idea to the physical part. The production process itself is quite slow, so it's not intended to be used for mass production. I told you for injection molding, we are ranging from like 2-3 seconds per cycle up to like in the range of minutes for very big parts. And here we are talking about hours for a single part. So that means if you intend to produce 1 million of parts, maybe 3D printing is not the right choice. So you would go for injection molding. But if you want to have a first physical part, you can have this very quickly. Compared to injection molding, you have to first design your mold, build your mold, do your first injection molding trials. It can be weeks and months before you get your first part. So that's the big difference and big advantage of additive manufacturing. Currently, there is still a limited number of materials, so you cannot use all the materials which are used in conventional processes. So for example, highly filled materials, glass fiber reinforced materials, is quite limited to use them. And also in general, the quality is not comparable with conventional processing. It means the surface quality is not the same, and also the mechanical properties are typically not the same. So it's more like for having a prototype, seeing how it looks like, also for maybe for repairing something. It would be a nice hybrid approach to produce something in injection molding and then doing some additional additive manufacturing onto it. It's a very nice and interesting method and process, but still there is a lot of development to be going on. 3D printing is not 3D printing, so there are a lot of technologies in this term 3D printing. I would like to just give you a brief overview. So you can first distinguish between different materials, so ceramic, metal, sand, plastic, wax, and also different technologies. I would like to focus today basically on plastic, of course, because that's what we were talking about in the whole project. And there we have 4 major processing methods with 2 principles. The one is parts being built through polymerization, so this one, basically resin-based. And then on the thermoplastic side, we have parts being built by melting. So that's the thermoplastic side. And there are also some effects on the properties. So I'll focus on these 4 methods here listed here in the red bar. First of all, the stereolithography principle. Basically, you have a liquid, a resin, which is a photopolymer, which can be cured by applying a laser. So what you're doing here is you have a platform. You start your platform here, then you have a liquid on it, which can be cured by using a laser. So at those positions where the laser contacts the liquid, here the material cures and becomes a solid, and the rest of the material stays liquid. So only on those local positions where the laser is acting, there we have some transformation of the liquid into a solid. And then step by step, the platform is moving downwards, and the next layer, some certain positions are cured, and then in the end, you can kind of create and grow such complex geometries. Another similar project is, or similar processing method is the photopolymer jetting. It uses basically the same principle of curing a material by using light, in that case, UV light. The advantage of this one is, in the first one, you had a container with one single liquid. So it's one material you can use. In this case, you're spraying this liquid onto a certain surface, and then locally on these positions where you spray it onto, you cure it by using UV light. The big advantage is you can use multiple containers of different liquids, of different materials, different nozzles spraying different materials onto each other. So basically you can create multi-material products. The disadvantage of this is it's based on thermosets, so it's on resins which are curing. So once again, in terms of recycling, once they are cured, these chemical bonds are established, you cannot remelt them and reshape them. Now we come to the thermoplastic part of it. So that's, the one is the so-called laser sintering or selective laser sintering. In that case, the base material which you are using, the raw material, is powder, a very fine powder, fine-grained powder in a container. So this is the powder supply, and then we have a platform. Then a very thin layer of powder is shifted to this platform, and then locally the powder is melted or fused by some laser. So here you introduce the laser power, and then locally the powder is melted together to a solid material. And then this platform moves down a little bit, and the next layer of powder is pulled here. And then locally, once again, on different positions, you can melt it, the material, and then you get this final shape. And then finally, we come to the method which we are also mainly applying in our institute. It's this fused deposition modeling, which is basically a brand name, or fused filament fabrication, which is the more general name of this principle. For that purpose, you first need to produce a filament with very tight tolerances of the filaments in terms of roundness and dimensions. And then this film is on those spools, and then you pull these filaments into an extruder, which is heated. So you basically melt this filament in this extrusion head, and then you, by layer, you deposit this molten film onto this platform. And then by that, layer by layer, you can create or produce your part. So the platform is going one step below, then the next layer of those filaments is put somewhere where you want to have it, and then it's going on like that. I want to show you just one example of a project that we did for this 3D printing, where there's a nice application for it. The project was called iPrint for implants from 3D printer. It was used for for replacement of bones of a skull which were damaged by an accident, for example. And it was a cooperation with the Medical University in Graz and Hage Sondermaschinenbau, who produced the printers. So basically the idea was to produce the polymer implants during the surgery. So the head is opened and then is measured, and then in the next room the printer works and starts to produce the spare part if you want so. And this could save a second surgery, because the normal procedure would be there is a big operation on the head, taking like the geometry. Then this geometry is transferred to an external company producing the spare part, which might take 1 or 2 days or something. That means in the meanwhile, the patient is closed again, and there is a second surgery for implementing the part. It can be tailor-made for each patient, of course. So depending on the geometry, it can be used. And it was nice. We got also an award for this project. And this activities are going on now. We are transferring this knowledge to other parts of the body, because the requirements for a bone on the skull is much different from a bone on the rib. So we have different material property requirements, and it's quite challenging. Okay, this brings me to the end. So I just tried to show you an overview of different processing methods and trying to summarize this. So once again, we start with our polymers. You need to know this chain structure, which has some effect on the morphology. So we have the distinction between thermoplastics, which can be further distinguished between and thermosets. Thermoplastics, once again, we have no chemical bonds between the single molecular chains, and thermosets, we have those chemical bonds which are irreversible. In the thermoplastics, we can distinguish between amorphous materials which are very unstructured and the semi-crystalline, where parts of the material are structured in a crystalline way. And for thermosets, if we have a tight network, we are getting duramers, very rigid materials. And if we have very few contact points, we are getting rubber. And this has an influence also on the processing methods. I showed you a little bit of different flow behaviors. So the shear viscosity is a function of shear rate. And for polymers, typically we have this shear thinning behavior, which enables us to basically do injection molding, so that if we're doing a very fast process, the viscosity goes down. And therefore we have a low viscosity, which is enabling us to fill small gaps. I showed you the principle of an extruder with the screw inside, heating it, melting it, and squeezing it through a die. And depending on the die, you will get different products. Either you can produce pipes, you can produce flat film, you can produce blown film, depending on the die and the follow-up periphery you use. I showed you the principle of blow molding. You have an extruder extruding a resin, which is then blown up and cooled down for a hollow body. I showed you the principle of thermoforming. You first need to produce a sheet or film which is extruded, and then this film is further deformed in this thermoforming process. I showed you injection molding for mass production of complex shaped single parts. And I also showed you the potential of additive manufacturing for individualized products and also fast development of products to get products very quickly from the process. So I want to thank you for your attention, and I'm open for any questions from your side, of course.
Thanks a lot, Professor Lucyshyn. Thank you for your very interesting presentation. It was extremely clear and very comprehensive. I see one question in the chat from Alejandro, who wants to know at which point in the polymer processing chain that typically additives are incorporated, so additives such as flame retardants, and how these affect the process or even the properties of the material. And he also imagined that there are differences between thermoplastics and thermosets. So could you elaborate on that question?
Yes, of course. I'm sorry, basically I forgot in this processing stuff to really go about compounding. So I was rather focusing on those processing methods which are really resulting in a final product. But basically all this adding different fillers is happening in a different processing step, which is before the real processing step. So this is called compounding. It's basically a mixing. So we have an extruder with typically twin screws, so 2 screws inside the extruder, which have a very good mixing effect. And there we are adding different additives to the polymer. And then in the end, the product of this process is basically pellets. And these pellets are then used in conventional processes to produce the real product. And there we can add different additives, can be solid additives, or particles can be liquid additives, and like flame retardants. So this can be added there. There is also an option to do it on a production machine. So you have kind of sort of master batches, as they are called. They have been compounded first into these master batches, and then you can add those pellets to the other pellets. You can kind of dry mix them and put it into injection molding machine or extruder, and then it will be kind of mixed together in this machine again. But still, the primary process of mixing happens in a compounder, which is a twin screw extruder. So 2 screws which have a very good mixing effect, but are not intended to be used for a production of films or whatever. And the effect of fillers is, of course, it changes the flow behavior. So if you add liquid fillers, it might reduce the viscosity. If you add particles, it might increase the viscosity. That all has an influence on the flow behavior. And in terms of the viewpoint of a processor, the best you would get is a material with very, very constant flow properties. And that's also the challenge regarding recycling. As soon as we're getting mixtures of different materials, different flow behaviors, our machines are really optimized for homogeneous materials. As soon as the material starts to be inhomogeneous, our processes will not run in the intended way. And there are 2 options. Either you tailor your material, you optimize your material so that it remains constant, but that's very difficult for recycling materials. Or the other way would be try to come to a flexible production method to react onto the polymer properties, to adapt your process to the properties of the material. That would be the more intelligent way, and something we are working on also. Is this question asked by that?
I believe so. Thank you. We also have a second question from Anne van Cetes. She says that in the beginning you made a distinction between elastomers and thermoplastics.
Yes.
What about the reprocessing or the recycling of thermoplastic elastomers? So which is a special case, of course.
Yeah, I would say thermoplastic elastomers, they are basically copolymers. So part of the chain are thermoplastic and parts are elastomer. And this can be, I'm not sure, I'm not an expert, I must admit, so I'm not focusing on this thermoplastic. I have not much experience on recycling of this, but I would say it should be possible to remelt them again, because the thermoplastic phase of this material is still able to remelt, and so it should be shapeable again. So I would expect that this should be possible to conventionally do mechanical recycling of that.
Okay, thank you. I see next question popping up from someone in the audience who is wondering if the additives, if they are mixed with a polymer material, not to be used like coating outside.
Normally not. So normally you put the additives into the bulk material and then it's extruded. So it's almost a homogeneous distribution of these additives everywhere in the material. So it's not like a coating. It can happen though that during processing or also in use that they're diffusing to the surface and then form some layers which you don't want, or you want them to have some protective effect. So it depends on your application, but typically they're distributed all over the material in the extrusion process.
Thank you. And next question from Tiago. So he points out that VOCs or odorous compounds are mainly formed during the extrusion process at high temperatures. And he wonders during recycling processes if, for example, washing procedures can be applied in order to diminish that. So is it possible to use washing, cleaning up processes after extrusion?
I would say if you have a look at the final product, so if you're extruding a film again or a pipe, the problem is that there's the relation between surface and volume is not the best. So you have a material, a product. With the washing process, you cannot reach into the product itself. So I'm not sure if the effectiveness is so high. So if you're applying washing in the pellet state, you have a better ratio of surface to volume, and therefore maybe you can easier extract some odors or something. But in the final product, if it's a very compact part for injection molding, for example, there will not be too much surface where you can extract something from it. So I would say it's more maybe in the stage after compounding and you have pellets before you go for the real production process. This would be a good point where you could maybe add some washing process. But in the final product, I'm afraid it's not so effective to do some washing of the product.
Mm-hmm. So typically, if I may add as well on that point, that during compounding, so they typically will also apply some vacuum there.
Yeah, degassing. Yeah.
Degassing indeed, to try to remove these compounds as much as possible. Okay, do we have any other question or point of discussion? We still have 5 minutes before the break, so you could put on your microphone if you would have some.
Okay, there's one question regarding degradation. That's the point I mentioned at the beginning. So we have this compromise between we need a sufficiently high temperature that we are able to melt it and to shape it. And on the other hand, we know exactly that each contact with heat damages the material. So what is basically done is there are additives which are added to the material with the only purpose that it survives processing. So not for application, so that's another topic, but really additives with the only purpose that they survive the processing step. So this is really a topic. And if you are recycling materials, so each processing step they are running through, they're damaged in a certain amount. So that means we cannot do this, although it sounds like very promising. You have thermoplastics, you can always remelt it and reshape it, but this is really limited by the damaging which you're doing to the material every processing step. There will be some damaging. In the first process step, maybe it doesn't make any difference. All those additives are consumed in this step, but then in the next step, these additives are consumed. And then that's the problem where the problem starts. If you add this again to a processing step, there might be more degradation. So what you can basically do is before you're doing recycling, you get recycling material, you still have to add another type of, or you have to add additives so that you can really process them again. So it's like upgrading them, or it's this additivation which is necessary to enhance the properties again.
Yes, that's also a question from Namrata. So indeed, she also mentioned that when you're degrading your polymer chains, that you actually are downgrading. And that she also wonders if you could, in the recycling method, that you could get these properties back to a certain level. And she asked if you could highlight what the difference between these two methods would be. But I think you answered that in your previous question.
Yeah, basically you add additives. I will tell a little bit also in tomorrow's lecture about this. And that's really, so just taking the recycled material and put it into the processing machine will probably not work quite well. Otherwise, you really have this downgrading, which you have, this downcycling, which we don't want. We also did a project where we used polyoxymethylene for a technical product, which is quite challenging. And in the end, by adding some additives, enhancing their thermal resistance and also mechanical properties, we ended up in really producing a product which is of the same quality or sufficient quality for the product, but is of pure recycling material. And this was really a nice result. I will show you this example tomorrow also in the recycling lecture.
Perhaps last question from Roberto, why can't thermosets be mechanically recycled?
Yeah, the problem is that you cannot reshape them. So you can grind them, you can cut it down to small pieces, but you cannot remelt them. So they're not deformable anymore. Once those bondings are established, especially for the duramers, they are not reshapeable anymore, because that's the principle for thermoplastics. You always have those entangled structures, you melt it and then it becomes movable, flowable. And if you have these fixed bonds, once you have these bonds established, the shape is given and you cannot change the shape anymore. So there are some attempts to break down those chemical bonds and to do some mechanical recycling, but to my knowledge, they're limited and not so easy to do. So but yeah, that's the main difference. So thermosets is really an irreversible process of those bonds, and then the material is not shapeable anymore.
Okay, Greg, great. Thanks a lot for your interesting lecture and answering of the questions.
You're welcome.
So then we will take a 10 minutes break, and 11:30, Professor Rahart will go into details on product development with recycled materials. See you in 10 minutes.
Yeah, see you.